Okay, yeah, thank you. Hi, everyone. My name is Jaehyuk Kwack. I'm from Argonne National Lab. Today I'm gonna talk about a geometric multigrid method kernel on Intel GPU with performance portable programming models. Geometric multigrid method is a way to solve the partial differential equation using a hierarchical approach. Coarse grids are constructed from the fine grid by agglomeration of fine grid elemental cells. It provides the order of n computational complexity, so it could be an efficient way to solve the problem. In this talk, I use HPGMG as my baseline code because it's very well written HPC benchmark for full multigrid algorithm. In general, GMG method has MGV cycle. It is composed of restriction from the finest grid to the coarsest grid, and then it does the bottom solve, and then it starts the interpolation from the coarsest grid to finest grid. In the restriction process, it has a smooth kernel in the level I and then residual kernel in level I. After that, it performs the restriction from level I to level I plus 1. And then it just repeats this process from the finest level to the coarsest level. Interpolation process, again, it has interpolation from level I plus 1 to level I, and then do the smooth kernel in the level I, then repeating this process from the coarsest grid to the finest grid. FMG cycle has a little bit more things. So first of all, it has restriction from the finest grid to the coarsest grid, and then do the bottom solve and the interpolation. After that, it starts MGV cycle for the level 2. After that, it has one more interpolation to the level 1, and then start MGV cycle for the level 1. Again, the interpolation to level 0, and then MGV cycle for level 0. So if we solve, this is example for the 4 levels, but if we have the more levels, we will just have the more MGV cycle blocks. So in general, this solution process, smooth kernel is one of the most expensive kernel. For example, to solve the 9 levels, 512Q problem, the smooth kernel time is more than 70% of total world time. So I extracted, as a first step, to investigate the performance portal version, I extracted the smooth kernel from this FMG cycle, and then one is in this series. So this is a basic structure of my mini app, initialization. And then I put the loop for iteration. This is not required, but I just want to measure the consistent performance, not the temporary performance. So I just keep repeating several times to get the consistent and sustained performance. At each repetition, it has loop for the series of the levels for the smooth in FMG cycle. So in the previous slide, I showed the example of the 4 levels. In this case, I solved the smooth kernel for this series of the levels. So level 2, 2, 1, 2, 2, 1, 0, 1, 2, something like that. So if we solve the larger level, we have more complicated series of the levels. For each level, we have loop for GSRB smooth, and this is solving the red part, black part, red part, black part. This loop cannot be parallelized because they have data dependency. But inside of the loop for the GSRB smooth, we have a loop for the blocks because each level has multiple blocks. So, and the computation for the multiple blocks can be parallelized. So in this talk, I parallelized this loop for the blocks for the GPU. Inside of the block, we also have another loop for the cells in the block because each block has multiple cells and those computations could be parallelized. But in this talk, I didn't parallelize that. So each GPU thread just perform entire blocks. In this computation for cells looks very simple, but actually it's not because inside the computation, you see the apply OPIJK inline function that is that complicated. So this kernel is not very simple microkernel. It has complicated data access pattern and then a lot of computation. So before we start, I just measured the baseline performance. The blue bar shows actually measured the smooth kernel time from the HPGMG. This is our reference. And the orange bar shows measured performance with my extracted mini-app with the same compiler. And you see they are almost the same. And in addition, I also tested my mini-app with Clang compiler. The reason is the compilers I'm going to use on the Gen 9 GPU are Clang based. So I just want to see what could be difference between the compilers. So You can see Clang compilers generate slightly slower executable, but I'd say they are in the same ballpark. Okay, so this is a SYCL DPC plus implementation. So from the previous structure of the mini app, I just put the red box or red word to represent the location of the SYCL implementation. So after initialization, I needed to start the create a queue for the SYCL, and then set up the buffers. And for the inside of the GSRB loop, I needed to submit a queue and add accessor, and then add the parallel 4 in the queue. So this is an update from the mini app to SYCL version. And OPENMP target uploading implementation, I did the same approach. So before and after computation, I transfer data from host to device and device host, and using the OPENMP target enter and target exit. And inside of the GSRB smooth loop, I just add only one line. So this is kind of a really attractive point of the pragma-based model, right? So you don't need to implement a lot of things. You just need to add appropriate pragma where it's required, right? So this is really a handy feature of the OPENMP model. So I just added pragma OMP target team distributed parallel 4 for the loop for the blocks. And then I measure the performance on Intel Gen 9 GPU and NVIDIA V100 GPU. So for this test, I used the testbed system in the Argonne, name is JLSE. JLSE has a lot of interesting architecture, as David presented before. In this talk, I tested this code on Intel Gen 9 integrated GPU and NVIDIA V100 discrete GPU. So before we start, Intel Gen 9 GPU, integrated GPU, is not intended for the HPC workload. It is just being used as a proxy development platform to try out a new programming model in advance of data center GPU being available. So comparison between the V100 and Gen 9 is not fair comparison, because the one is discrete and very many SMs, and the another is integrated GPU with less EUs. But still, Intel Gen 9 has a very similar base unit, which is EUs or sub-slices and slices. So probably understanding performance characteristic on the Gen 9 GPU is good to understand the characteristic on Intel discrete GPU in the future. So this is a simple comparison. The double precision peak flop rate is 7.8 teraflop and 0.33 teraflop. So approximately we have 24x difference between the Iris and V100. And GPU memory bandwidth, the Gen 9 GPU has 2 layers of the memory. So DRAM is large capacity memory, and EDRAM is small capacity but the faster memory. So if your kernel uses the DRAM mainly, the difference between the Iris to V100 is the 26x. But if your kernel can use EDRAM efficiently, we can expect only 12 difference between the V100 and Iris node. For SYCL DPC++, I use public LLVM SYCL with the CUDA backend for the V100, and on Iris I use Intel Beta 9 DPC++ compiler. For OPENMP target compiler, depending on the host CPU, I use the Clang OPENMP compiler and the IBM XSC compiler. And the Iris node, I use Intel Beta 9 ICX compiler for OPENMP uploading. Before we start, we also need to think about what could be the configuration for the GPU. So since this code use parallel, this code has parallelized the loop for the blocks. So we had better have many numbers of blocks instead of a large size of block. So this is default configuration, but this block is quite big because of the number of blocks is quite limited. So I changed the type configuration. So as we move from left-hand side to right-hand side, we will have more blocks for the loop. So we will have a better chance to get performance. So this is a SYCL performance for the exactly same source code. I just use a different compiler and different architecture and just ran it. So this is word time, so lower is better. So for the big size of the blocks, which means the less number of blocks, we have a lowest performance. As we decrease the size of block and increase the number of blocks, so we have the better performance here. So trends are very similar to each other. And I also tested with OPENMP uploading compiler. So in Intel case, we see very similar behavior in here, but this is actually unexpected because I had really good experience with OpenMP compiler on the NVIDIA B100 GPU with another application. But in this case, for some reason, LLVM compiler and XLC compiler, both of them give me a runtime error. And I didn't really look into the issue, but I think possibly using the pointer inside of the target region could be some problematic with some compiler. So I generated some quick reproducer, and I will talk about it at the end of this talk. And I want to know, before I just compared the double precision peak and the bandwidth peak, right? So I want to know whether my kernel is memory bound kernel or compute bound kernel, because I want to. So in the previous case, I can show the portability of the SYCL between the different architecture, but I don't know whether this is performance portable or not. So before that, I want to know what is my kernel looks like. So I just used a divisor roofline feature on Intel Gen 9 GPU, and I tested a 256 cube grid with a 2x2x2 configuration. And as you see, and the OpenMP and SYCL shows very similar result. And L3 is very close to L3 loop, and GTI is very close to GTI loop. So which means my code is using EDRAM, not the DRAM. So the comparison between B100 on the Gen 9 GPU with my kernel should be based on the EDRAM based. So from this figure, I can say, oh, my kernel is fairly memory bound kernel. And then I compare the result. So compared to single Skylake core performance, B100 GPU shows 40x speed up, and Gen 9 case, OpenMP and SYCL, both of them shows around 4x speed up. OpenMP is slightly slower than SYCL, but the difference is less than 10%. So I would say they are almost similar to each other. So in this case, if you compare, if you compare the B100 and Gen 9, we see the around 10x speed ups, and this is reasonable speed up because the kernel is identified as a bandwidth bound kernel. And this is a reproducer to investigate the issue. So in this sample code, I just make an array, n-cube array, n-scale array, and initialize on the host and copy back to the device. And in target region, using this the pointers, I updated the numbers and then copy back to host and check the result. So with this simple kernel, with XLC compiler, I could get the correct result with a runtime error with up to 1102 scale array. With Clang, I could get around 22,116 square array, and ICX I can go a little bit larger. So I'm not saying this is the only reason I cannot get the result from the NVIDIA side with OpenMP compiler, but that could be one issue. And even with this simple code, OpenMP target offloading compiler can have different capacity to handle the array with pointers. So OpenMP specification may be perfect, but depending on who's implementer, you may have some challenge to get your performance portability. So this is conclusion. I extracted the smooth kernel from HPGMG and I implemented that mini-app with SYCL and DPC++. With large number of blocks, this version shows a meaningful speed up on NVIDIA B100 and Gen 9 GPU. I also implemented it with OpenMP target offloading model and successfully built and tested on Gen 9. Some issue is on the NVIDIA B100 GPU, and seems like some compiler has different capacity to handle the array with pointers in the target region. So my next step is I plan to fully implement HPGMG with the SYCL. It will take time, but I will do that. And I will also investigate OpenMP uploading test with other compiler, PGI and the Kwack compiler. And also the Cocos implementation is working in progress. So thanks for support to ALCF and ECP and also JLSE system. And I also thank the Ken Moffat from Intel for reviewing the data and provide feedback for this talk. And this is all for today. If you have any questions.